Hello, welcome AP Calculus students. This is your first notes video. Section 2.1 in our book, Chapter 2 is about limits, and Section 2.1, being the first of those sections in that chapter about limits, is an introduction to limits. The first thing we need to figure out is what exactly is a limit. What does this mean? And I suppose you might also be wondering, as soon as we talk about what they are, why we are interested in them. But we'll leave that discussion for another time, I think. Right now we'll just try to figure out what they are. So let me introduce you to some notation. This is how we write limits. The limit as x approaches some number here, and typically when we just want to be general and we don't want to specifically pin ourselves down to a number, we want to leave open the possibility of it being, say any numbers, in the same way that x is a variable. C will be our constant here. So as x is approaching some number c, whatever c happens to be, of some function f of x, this is a limit. What does this mean? This means as x gets really close to c, what happens to f of x? And the answer to that question is what this limit is equal to. We read this, I'm going to write it next to here, we read this like this is the limit as x approaches c of f of x. That's how you read this. The limit as x approaches c of f of x. And again, that's asking, as x gets really close to c, what happens to f of x? So I think there's no better way to get into this than to just kind of look at some examples and try to figure out what the heck this means. So here's an example. What is the limit as x approaches 2 of x squared? As x approaches 2, what's happening to this? As x gets really, really close to 2, what's this getting really, really, really close to? Well, this is a particularly uninteresting example, because to see what happens to this as x gets really close to 2, you just have to plug that in. So it doesn't really take a whole lot of thinking about, maybe good to think about it a little bit here, what this really means. As x is getting really close to 2, x squared is getting really close to 4. That's not really the kind of limit that we're going to be particularly interested in. We're going to be interested in ones that are a little bit more, well, let's say interesting than this. All right, so that's the basic idea. In this first section, 2.1, we really want to focus on just sort of an intuitive understanding and more maybe graphical understanding or visual approach to understanding what a limit is. So let me make you another example. I'll make if you had to say what kind of function you think that is, we'll just have that be scaled by 1s. You probably think that that's an absolute value function, right? And it is. You might, if you want to, give yourself a little brain teaser. What is the equation for this? It's not that hard to come up with. You can pause and do that if you want. So I'm going to ask you just some questions about limits based on this graph. What is the limit as x approaches 1 of f of x. We'll call this function, this is the f function. What's the limit as x approaches 1 of f of x? Well, as x approaches 1, as the x values get closer and closer to 1, it looks like the y values get closer and closer to 0. Right? Because the point 1, 0, it's right there on the graph. So, I mean, it's kind of an uninteresting one like the last one. It's just right there. All right, how about this? What's the limit as x approaches 0 of f of x? What do you think that is? You can pause and think about that for a second. Look at that graph. If you thought that as x gets closer and closer to 0, looks like the y value is getting closer and closer to 1. In fact, it is 1 there, right? When you get to x equals 0, the point 0, 1 is right there on the graph. Right? Well, it's not too terribly interesting, but maybe it'll help us understand a little bit better what's happening. Well, here's one that's a little bit more interesting. Let's say we have a function that looks something like we had before. It looks like this. You might have learned, I suppose in pre-calculus, maybe a little bit in Algebra 2. This is what we would typically call a piecewise defined function. This is made up of two sort of separate pieces. A piecewise function, they don't have to be separate, they can link up, but it's made up of these sort of seemingly unrelated pieces. So, what is the limit as x approaches 1 f of x? We'll call this one, this will be our new f of x function. Let's see, as x approaches 1, it looks like our function is approaching 1. And that one, there's no problem there, right? As x approaches 1, looks like the y values are approaching 1 too. But what about, what's the limit as x approaches 0 for f of x? As x approaches 0, it looks like, well, we got a problem here. On one side, as we approach it from like x values that are above 0, as we approach it in this direction, it looks like it's trying to get closer and closer to 0. The y values are getting closer and closer to 0. But as x approaches 0 from underneath, from values a little bit below it, it looks like the y values are getting closer and closer to 1. So what we say here, if a limit is trying to be two different things on two different sides, we say that that limit does not exist. And if you've ever seen the movie Mean Girls, well, there you go. The limit does not exist. Remember that at the end? It's a good movie. It's got math in it. All right, now, we don't want to completely abandon this, though. There is still something going on. I mean, it's still approaching something on this side and something on this side. So here's how we deal with this. I can say, and this is how we notate, up here where you would put an exponent usually, I'm going to put a little plus there. What that means is the limit as x approaches 0 from above. The plus means from numbers that are a little bit bigger. So that means this way. So what's happening as the x values get closer and closer to 0 from this side? What's happening to the y values? Well, they're getting closer and closer to 0, right? Getting closer and closer to this. Now, you might object here and say, well, wait a minute. It never actually gets there because there's a hole in the graph here. But it does not matter. What matters is what is it getting closer and closer and closer to. If it happens never to get there, that's okay. The limit is still what the destination looked like it was going to be. The fact that when we get here it jumps up to there, it does not matter. You follow this line down, it looks like you're headed for right here. And that's a really, really important idea, because the kinds of limits that we're going to be interested in are the kinds of limits typically where you don't actually get to that destination. So you've got to get used to that idea that it doesn't matter what happens when you actually get there if you never get there. If you do, like all these other boring examples that we did before, well, that's fine. But the interesting ones, turns out, are ones where you don't actually get there. Now here, on this side, we have the limit as x approaches 0 from below, so I put a little negative there to indicate that I'm coming at it from below. And here, on this side, it looks like we're getting closer and closer and closer to 1. The fact that there is actually a point there doesn't matter. There could have been another open circle. It could have been another hole there. It's what we're getting closer and closer and closer to. It's what it looks like the destination is going to be, not what happens when it gets there. All right, so let's recap here. If a limit is two different things on two different sides, then we say that the limit does not exist if we do not specify here, right? What's the limit as x approaches 0? Well, I don't know. It's 0 on one side and 1 on the other, so we say that that does not exist. If we're willing to go ahead and put a plus or a minus here, then we can talk about each side, and we call these one-sided limits. It's one thing on one side, one thing on the other side. So we can talk about those, but if we don't specify, well, it can't be both, right? So we have to say that it doesn't exist. All right, here's another example. Let's take something that looks like a parabola. Maybe it reminds you of the y equals x squared parabola. But this particular parabola, there has a hole here at the origin, and then where it seems like that point should have been, there is maybe somewhat surprisingly a point here in this other spot here. And maybe we should just pause for a second, not literally pause the video, but maybe we should stop and think about and talk about, like, maybe you're thinking to yourself, okay, you're just making up really weird examples here. Like, this kind of thing doesn't really happen, because like usually that point's in the right place. Well, maybe that's true, but all these examples are going to illustrate things that we have to be able to deal with. And I will emphasize again, the kinds of functions or the kinds of limits that we're going to be interested in are ones that have weird things like this going on. Why is it that all of a sudden we'll be interested in weird stuff like this? We will deal with that question later. So, so here it is anyway. I might ask you first, is this in fact even a function? Do I really have any business calling it f of x and saying that it's a function? Well, the answer to that question is yes, right? Because it does, if you're thinking like vertical line test, it does pass. There is a weird hiccup there, but it still is not any problem for it passing the vertical line test. So it is a function, indeed. So here's a question. What is the limit as x approaches 0 of f of x? What is this limit? Well, on this side, let's say what's happening as it gets closer and closer to 0 from beneath. What does it look like the destination is? Well, as x gets closer and closer to 0, it looks like y is also getting closer and closer to 0. It's getting closer and closer to the point 0, 0. We say that that limit is 0. And if you're thinking, but wait, but the point's up here, it doesn't matter. What matters is what we're getting closer and closer and closer to. So this point could be up here, here, down here. It does not change what this answer is. The limit is about what it's getting closer and closer to, not the actual destination, not what it actually is. when we get there. How about on the other side? On this side, as we get closer and closer and closer to 0, the x's get closer and closer to 0, the y's also get closer and closer to 0. It looks like that's going to be our destination. Right? So look, both sides are the same. So the limit as x approaches 0 of f of x is 0. In other words, I can make this stronger claim, which really says that the two sides are the same. Right? The limit as x approaches 0 of f of x is equal to 0, because the two sides were the same. Right? And even though this point was actually at 0, 1, notice that none of these were about the 1. It was all about what we're getting closer and closer to. Now, what about a function like this? This is a function that has a vertical asymptote. Right? And we'll say that that vertical asymptote is at 1. So here's our f of x. Looks like this. You've seen functions like that before. Some kind of rational function, maybe. So let's see. What's the limit as x approaches, looks like 1 is where the asymptote is. So how about 1 from below of f of x? So as the x values get closer and closer to 1 from below 1, so that means this side, right? As it gets closer and closer to 1 from underneath, what's happening to the y values? Well, it looks like as we get closer and closer to this, it's blowing up. They're getting bigger and bigger and bigger and bigger. So we say that this approaches infinity. You might object, I think I would probably object if I were you, and say, well, wait a second. I mean, how can infinity be a limit? I mean, the fact that, like, the limit is infinity might sound sort of oxymoronic. And I think you're right if you are making that objection. But you'll see in a minute that we do write infinity here instead of does not exist, just to clarify, just so we can capture as much information as possible. Let me try to explain here how we're doing that, or why maybe it's better to write this. So on the other side, as x approaches 1 from the positive side, what's happening? Looks like we're plunging down to negative infinity. As the x values get closer and closer to 1 from above, looks like we're going down to negative infinity. So on one side, we're going up to positive infinity, on the other side, negative infinity. So this kind of captures some information about what's happening at that vertical asymptote, rather than just saying, oh, it doesn't exist. That's why we do it that way. Now together, here's the limit from the negative side, here's from the positive side. So what do you think the answer should be? What should we report if it just looks like this? If you're not sure or want to think about that for a second, I always would encourage you to pause the video and stop and look and think about it. So if you've thought about that now, since this one is infinity and this one is negative infinity, since they're two different answers, we have to say that without the clarification of which side, that this does not exist. So this one's infinity, this one's negative infinity, but here, if we just say the limit as x approaches 1, because it's doing two different things on two sides, we say that the limit does not exist. The limit does not exist. And I think that these examples should carry you through the assignment for section 2-1. I think that that should be enough information for you. I might just point out that if we wanted to sort of look back at what we did, the interesting things seem to happen when functions have holes in them, breaks like this, or what we'll call a jump. It jumps suddenly from one value to another, or vertical asymptotes. Holes, jumps, vertical asymptotes, like the Wizard of Oz. Oh my. So there you go. There's your first set of notes, just about 20 minutes. See you in class.